So last time I formulated the so-called SARD theorem. I will write the statement on the board. But first let me say that in differential topology, and not only in differential topology actually, it is very often that we assume that some, well, map or set or whatever is this, people prefer to say, is in general position. For example, you have a curve in space. Yes, a curve in space. Certainly it may happen that it has self-intersections. But usually it doesn't have self-intersections, which means, for example, that if we take an arbitrary curve and very slightly perturb it, all self-intersections will disappear. The same is true for curves in the plane. Actually, certainly curves in the plane do have self-intersections, like figure 8. But again, we have a tendency to assume that these self-intersections are isolated and transverse. That is, a point, there are two strands, two portions of the curve which pass through this point, and they, if the curve is smooth, they are transverse to each other. And we can say that never no triple points, never three intervals on the curve share a point. It is very often that we want to assume that. And you can say many times that it is obvious, geometrically obvious, why not, or something. But still, there exists a theory, general theory, which is directed to this removal of, how to say, non-generic singularities. There are different statements in analysis, although they usually can be found in textbooks in differential topology, but certainly they belong to analysis, which can serve as a ground to this general position theorem. The most classical of these theorems, although it is not always sufficient to achieve the general position for a map, whatever, is the so-called SARD theory, which I formulated last time. So we consider a map F, smooth map. Smooth means C infinity now, between two manifolds of some dimensions. Actually, M will not be important to me in this statement, but N will be important. Now I say that a point P in M is critical, that is critical point of this map, if the rank of the differential of the map F at this point, which is linear map between two spaces of dimensions M and N, if this rank is less than N, or the same as to say that the image of this map T Pm is strictly less than the target space where Q is f of p. This is definition of a critical point. Then there are other definitions which are based on this definition. First, if a point is not critical, then it's called regular. Then a point Q in N is a critical value of f if q is equal to f of p, where p is some critical point p is a critical point of f. And again, non-critical means is abbreviated as regular, so a point in n is a regular point for f, a regular value, excuse me, for f, if it is not a critical value. Last time I tried to say to you how ridiculous this language is, because, for example, if dimension of m is less than dimension of n, if small m, small case m is less than small case n, then every point of m is critical. Another ridiculous feature of this terminology is that if a point is not a value of f at all, doesn't belong to the image of f, then it should be counted as a regular value without being a value. For example, again, if the dimension of m is less than the dimension of n, then all points in M are critical. So all points in the image of this map F are critical values. And in this ridiculous case, a point in N is a regular value, even only if it is not a value at all. What about that? Any questions, remarks? Now the fact is, certainly we prefer that a point is a regular, that a value, a point in N is a regular value, because then also many properties in the neighborhood of this point, of this value, hold. But we never can say that an arbitrary map F has sufficiently many regular points. For example, if your map, the most obvious map is constant, just the whole manifold M is mapped into one point of N, then every point in M is a critical value. So no upper estimate for the set of critical points, but the set of critical values in many respects is thin, small. And this is precisely what the Sard theorem says. There are several, not equivalent, but equally useful for us for statements of the Sard theorem. I will mention two. I mentioned them last time. So, theorem. It was proved in the late 30s. Theorem. For absolutely arbitrary map F, the set of critical values, this is the set, critical values, is small. And there are two different senses in which it can be so. First, it has measure zero. Second, it is a union of nowhere dense of countably many nowhere dense closed sets. more common to say that the set of critical, the second statement, the set of critical values is the countable intersection of dense open sets. This is precisely what this statement means. In many cases, it will be sufficient to us to know that actually there are regular values. Just the set of regular values is non-empty. Or regular values is non-empty, yes. Sometimes it will be useful to us to know that the set of regular value is dense. Set of regular values is dense. This statement is more precise. Last time I mentioned, and this will have zero importance for us, that a similar theorem has for manifolds and maps which do not belong to the class C infinity. Then we can consider maps belonging to some class CR, that is, coordinate functions have R continuous partial coordinate functions have continuous partial derivatives up to the order R, CR. And the same theorem holds in the class CR under a condition that R is greater than the difference of dimensions, than n minus m. Then, m minus n. So if m is small and n is big, that's okay. We can take any smoothness. C1 is sufficient. If, however, we have a map of manifold big dimension and manifold small dimension, then to apply the theory, we need that the class of smoothness is sufficiently large. Since I consider only C infinity maps, this fact will not be important to me. It becomes important if you consider proof of the theorem. As to the proof, I will not give it. It is contained in some textbooks in differential topology, and I actually included proof of it, taken mostly from the book of Milner and Stashev. Yes, it is presented in an appendix to my notes, so 2 or 3 pages in the measure statement, and it actually uses some facts from analysis. I think the most least trivial fact from analysis which this proof uses, I don't know how much you know it. It is an important theorem from analysis, so-called Fubini theorem. Have you heard of this? You know this. The theorem states, well, at least certainly it can be stated as a theorem about integrals, but for measures, it states that if we have, for example, in the plane, but it is actually any dimension, if we have a measurable set whose intersection with any vertical line has measure 0, then it also has measure 0. You understand? This is how this theorem is stated in textbooks and analysis, and how it is used in this form in the proof of the Sard theorem. Although I will not prove the theorem, I still want to say that there is one trivial case. This theorem certainly is a deep result only if m, the dimension of the source manifold, exceeds n, the dimension of the target manifold. Then this theorem has, how to say, very much non-trivial proof. Well, non-trivial, 2 pages. But if the dimension of m is less than or equal to the dimension of n, then this theorem becomes almost obvious. And I will say several words about the proof of this in this case. The more so sometimes and in very, very important for very, very important results, we will need precisely the theorem in this case. So, the proof for the case when M doesn't exceed n. So a small manifold is mapped into a big manifold. My first remark actually is valid not only in this case, in general case. I want to say we have two manifolds M and N, and they both have countable atlases. U, I, Vi, Vj, Cj. Two countable atlases of this, countable of these two manifolds. Then, for any pair ij, we can consider the following. We can take the set Vj, it is set in Euclidean space. We can map it into our manifold, and then we can take its inverse image. We can take its inverse image in Rm. Then certainly we have a map of this no, F should be here, excuse me. So I want to consider for pair I and J, this is Ui, this is Vj, and I want to consider those points. So I consider Ui and Vj, I apply Phi and Cj to them, and this is subsets of M and N. Then I consider those points in Ui whose images belong to Vj, images with respect to the map F. Yes? And for every pair I and J, this gives you a map of some open set in Rm into Rn. There are countably many such maps because there are countably many pairs ij. And this map has its critical values. So I have the set critical values ij of f. And this set belongs to Rn actually. This belongs to n. And the set of critical values of f is the union of all these sets. So Vij are critical values of this map, Vij. It is sufficient to prove that this has measure 0. Because a countable union of sets of measure 0 is again a set of measure 0. If so, then this shows that actually this theorem formulated for manifolds and everything should be proven for maps between domains in Euclidean spaces. Moreover, certainly we can assume that all sets Ui are bounded. You know, charts can be defined in such a way that they are defined on bounded open sets in Rm. So in this respect, so this theorem is not only in the case when m is less than or equal to n. In general case, the theorem is reduced to the case when no manifolds are mentioned. We have some smooth map defined on a domain in Rm with values in Rn. It has critical values, and the set of these critical values has measure 0. This is my first remark. What about that? If no remarks regarding this, then I turn now to the case when m is less than or equal to n, and we'll prove everything. So this remark can be formulated in such a way. We can assume that m and n are bounded domains in Rm and Rn. This is m, this is n. Let me begin with the case when m is equal to n. It is actually the most complicated case here, but it is very easy to prove the theorem in this case. So look, let them be so the same dimension. Then we have this map F, and there is Jacobian matrix and its determinant. So there exists a function, determinant of the Jacobian, m in R. What is the critical point of F? The point where this function is 0. The critical value is the point which is the image of some point. This is a continuous function, certainly more than that, smooth function. So this is the set of critical points. This is the set of critical values. Consider now the set where the determinant of GF is less than some positive constant epsilon. It is an open set, right? A bounded open set. Consider its image. Its image contains this. This is the set image of this set. Now, what is the volume of this set? You see, if the determinant of the Jacobian, better to say actually absolute value. If the absolute value of the determinant is less than epsilon, then locally at every point, this map multiplies the volume as a number which is less than epsilon. So the volume of the image is less than epsilon times the volume of the set, right? So we have the following. Let me write it here. We have the following. The measure of critical values of F doesn't exceed the measure, the volume, because, well, right measure of F of the set this is at most epsilon times measure volume, now because it is an open set, of this set. And this is less than or equal to epsilon times the volume of our domain, which solves the problem because epsilon is arbitrary. So we see that the measure of our set is less than epsilon, arbitrary epsilon, times some number, which certainly means some positive number, which certainly means that it is 0. No positive number may have this property. So this is done. This is done in the case when m is equal to n. The case when m is less than n, in many respects, geometrically is easier. But I prefer to prove it easy, again, a ridiculous trick. So if m is strictly less than n, then I replace the map f by the map m times n minus m, where this is a compositional projection of this onto m. That is, the second factor doesn't participate in this map, and this is f. Certainly, everything is the same for this map. Actually, the set of critical values, which is the same as the image of this map, because the dimension of m is less than the dimension of n, is the same as the set of critical values of f. By this reason, it has measure 0 by the previous theorem. Certainly, it is, again, a ridiculous way to prove the theorem, because actually the case when dimension of m is less than dimension of m, the statement is more obvious. It means more or less that if you have, for example, a smooth curve in the plane, it cannot fill the whole plane. Certainly, there is, again, such a strange thing as piano curve, which actually is a curve which fills the whole plane, inertial space away in dimension, but you should take into account that it is not smooth. Continuous, maybe, but not smooth. And by for smooth maps, for smooth curves, it is obvious. It's very easy, can be proved by elementary means of analysis, that a smooth curve can never fill a planar domain. And the same is true in arbitrary dimensions. This is precisely what the theorem states in this case. I think it is all I wanted to say now about the third theorem. So if you have questions, let me say this is an important theorem. Even if you don't care of manifold differential topology, still it is an important theorem, important result. However, trivial from the point of view of proofs it may seem. By the way, Sard, this was a student of Morse. We will consider here Morse theory, so you will know a lot about Marston Morse, great American mathematician. And Sard was his student, and as far as I know, he proved the theorem when he was a student. And as far as I know, he has never proved anything significant in the future. I met him once. He was an old man, had a talk, which I attended, but nothing interesting. Sard's theorem, which everybody knows, so the name is known to everybody. Actually, this Sard was prove the theory. Certainly, there he shared this result with some other people. So sometimes the theorem attributed not to Sard, or at least not only to Sard. I will not mention that. You know, it always happens in history that every result is shared by several people. If you don't have immediate questions, then I will continue. There is, again, an important, well, I will show some immediate application of the Sard theorem. And looking at the watch, I'm not sure that I will be able actually to reach the point where the theorem is needed today, next time certainly. I will try. But there are embedding theorems in topology. Classical domain in topology, I can only boast that this was my actually first thing which I studied in topology, and my first work was related to this. So, suppose that we have a manifold. Our definition is very abstract. Then we consider examples. Spheres, projective planes, so on and so on. And at some moment, we discovered that actually there are many manifolds because there are submanifolds of Euclidean spaces. So whatever you can imagine in Euclidean space of any dimension, such smooth surface of any dimension, you will get a manifold. It is interesting, agree please, that are there manifolds beyond this example? Or actually it is all? Which means, is it true that every manifold at all is well diffeomorphic to a submanifold on Euclidean space? We can say the same in a different language. Is it true that every manifold can be embedded into some Euclidean space? You say yes, because you know, or because you guess. And you do not say, or you want to say something about this? You do?
Probably not.
Probably not, you just want to. So there are manifolds which cannot be embedded in Euclidean space, in the Euclidean space. I understand your point. I understand your point. But still, the result is correct. Every manifold can be embedded into some Euclidean space. Dimension. Then we can try to enhance this statement, dimension-wise. Suppose that our manifold has dimension n. Maybe m is m. It's not important. If it can be embedded into some Euclidean space, that what can be said about the dimension of this Euclidean space? About the dimension of this Euclidean space. And there is a very classical, in some sense not too well, easy to prove, but I prove it here. Result belonging to Whitney. Hustler Whitney is an American topologist who actually was one of the creators of differential topology in the form in which it is represented here. So it is a theorem which is attributed to Whitney that every, listen, n-dimensional manifold, whatever it is, can be embedded into the space of dimension 2n plus 1. This is the most classical result of this theory obtained in the 30s, and together with many other results belonging to Hustler-Whitney. You understand? For example, one-dimensional manifold can be always embedded in R3. There was a problem in my problem set that everyone were connected. One of a manifold is either a line or a circle, and both can be embedded into R2. But Whitney theorem says R3. Actually, it says more. Suppose we have an arbitrary smooth map of M into R to n plus 1. Then it can be approximated in the C infinity sense, approximated by embeddings. Imagine a curve in space. By chance, it can have self-intersection, not necessarily an embedding. But just perturb it a little bit, and you can obtain an embedding, a curve without self-intersections, an embedded curve in R3. And the same is true for in any dimension. 2n plus 1 here is the right estimate if you want to have approximations, to have this enhanced result. But I already said to you, and who can doubt, that actually any one-dimensional manifold is embeddable into R2, and 2 is 2 times 1 if you don't know. What about two-dimensional manifolds? For example, projective plane, not embeddable into R3, but it is embeddable into R4. The same Whitney, 10 years after his first, the theorem, I said first, I'm not sure that it was his first theorem, the same Whitney, 10 years after, in the 40s, proved this theorem that every n-dimensional manifold has an embedding into R2n. The example of projective plane shows that we cannot hope to go further, to embed a manifold of dimension n into the space of dimension 2n minus 1. But you see, projective plane is something very special. There are other results much later. For example, every n-dimensional manifold can be embedded into R2n minus 1 if at least one of the following two conditions hold. First, if n is not the power of 2. If n is not the power of 2, then any n-dimensional manifold is embeddable into R2n minus 1. It is true. If the manifold is orientable, then again, it is embeddable into R2n minus 1. There are many results. It is an extensive theory, which certainly will not consider here. And I cannot say that it is finished. There are manifolds, even among projective spaces, for which no estimate is known, no precise estimate is known. So maybe I just want to guess. If you take the space RP50, the 50-dimensional projective space, then probably, which I cannot say precisely, then probably it isn't known what the smallest dimension is, such that RP50 can be embedded into the space of this dimension. It is slightly better for immersions, but I will not study the subject. So I formulate the theorem, and certainly I will not be able to complete the proof today. So I will say more or less how it is proven, and then next time I will consider the proof in all details. So the following fact, theorem. Let M be a compact, I'll do the second part now, be an n-dimensional manifold. Then, statement 1. Every C infinity map M into R2n plus 1 can be C infinity approximated by embeddings. By smooth embeddings. B. The thing is always the same, so I here R2n. And here emergence. Every map of R of M into R2n plus 1 can be approximated by embeddings. Every map of M into R2n can be approximated by immersions. You remember I wanted to say compact. And then I say that actually the theorem is true in this form. But my proof, I will consider only the case when M is compact. Otherwise, we will have to deal with infinite dimensional spaces, which may find not very convenient. So there are ways how to prove it for an arbitrary manifold necessarily compact. You can think of this, but I will not touch this subject. Now let me say briefly, let's discuss together how the theorem can be proven. First, let us forget this dimension n plus 1. Let us try to arrange an embedding of a given manifold in the sub-Euclidean space, whatever dimension it is. My friends, what is actually a map of a manifold, of an arbitrary set into R capital N? I think that this is just a set of real functions, right? What is a map into the plane? Two functions, right? X coordinate, y coordinate. What is a map into R3? Three functions. X coordinate, y coordinate, z coordinate, right? Coordinate functions. So a map, a smooth map, yes, of a manifold into Euclidean space is just a set of functions. Finitely many. Compactness will take care of that. But if you want that it is not just a map, we want that it is an embedding, then in particular we want that no two points have the same image, right? This means that we have, for example, we have a manifold of some dimension. We want to embed it into R1 million. So we need to construct on this manifold 1 million smooth functions. 1-to-1 means that for no 2 points of our manifold, all these million functions have take the same values, right? Sounds actually very plausible. Certainly, if you have one function, it's possible that it takes the same value at different points. But many functions, much more than dimension of manifold, then probably we can arrange this family of functions in such a way that for every 2 points, at least one of the functions will take different values. How to do that? The best way to do it is first consider local coordinates. Certain local coordinates are very much local. But we have a theorem which allows us to extend every function to the whole manifold. If a function is given on an open set, then it can be extended to the whole manifold from any subset, open subset. So if a function is given on U, we can extend it to the whole manifold from V, where V is another open set, such that V bar is contained in U. From any such subset we can extend. In this respect, we take local coordinates, and there are finitely many of them because compact manifolds, so finitely many charts, finite atlas. for every chart there are n functions, local coordinates, and we get some family of functions given on the whole manifold. Finally, many. The number of functions is the product of the dimension of manifold and number of charts. Do these functions separate points? Yes, if we consider them within 2 points within one chart, within one domain of local coordinates, right? Every 2 points have different coordinates. At least one coordinate is different. But if 2 points belong to different charts, then it is not clear that all functions which we construct will have different values on them. Very plausible, but still we need to do something to be sure. Before that, I want to say that if you want to construct an immersion, not an embedding, then what I said is enough. That these functions locally, they will provide embeddings, embeddings of domains of local coordinates into Euclidean space. So that it will be an immersion. And when to get an embedding, we need to extend the number of functions. We also need to find functions which separate points in different domains. This is done by a very simple trick, which I will not. So big dimension, say it is achievable. Now how to make the dimension smaller? What to do? We have say 5-dimensional manifold. And we embed it in a manifold of dimension 1000. How to embed it in a space of small dimension? How to reduce the dimension? Imagine that you have, say, a curve in R4. What do you do? You just take a projection into R3 and choose the direction of projection in such a way that this embedding remains an embedding. It's always possible. This is precisely what I do. I take a 50-dimensional manifold embedded into R1000. I take all pairs of points in this manifold. This is also a manifold of dimension 100, right? M times M, set of pairs. For every pair, I have a line. I have 2 points in R1000 and a line through these 2 points. And I don't want that my projection acts in the direction of this line, because in this case, these 2 points will collide in R999. So some directions of projections are prohibited. How many of them? And this is the image of some map of M times M into our Euclidean space. M times M, if M is 50, has the dimension 100. If my space has the dimension 1000, then it can take such a line there, which is not parallel to any chord, to any line which passing through 2 points of the manifold. And apply the projection. Third theorem will readily say that a smooth map of a manifold of dimension 100 into R1000, its image is not the whole space, actually in the projective space, because we're interested in directions. This map is never onto, and we can find a direction in which we can project. Then again and again and again, until the dimension of M times M becomes equal to the dimension of the set of all directions. This happens precisely when the space in which our manifold is embedded is 2n plus 1. This is how the theorem is proved, and you see now where the third theorem in its actually most trivial form is used. Next time I will present this proof in all details, so you will like it. Thank you.